those hybrid orbitals are still on the particular atom. They don't look like the S and Ps that we're used to. And so that hybridization theory works for a whole lot of things, but it doesn't work for everything. If we look at oxygen, for example, oxygen, because if we drew out the Lewis structure for oxygen, well, we'd see a double bond and we'd see two lone pairs of electrons on both oxygen atoms. We've drawn the Lewis structure of oxygen before. And it doesn't seem like there would be any unpaired electrons in an oxygen molecule. And yet, oxygen behaves paramagnetically rather than diamagnetically. And so I'm going to share my screen here. And this is a little YouTube clip about the magnetism of oxygen.
Frostbite Theater presents Cold Cuts, no baloney.
Just science.
Can you hear it?
Hi, I'm Joanna.
And I'm Steve.
And this is a test tube of liquid nitrogen.
And this is a test tube of liquid oxygen.
Let's see what happens when we pour the liquids past the poles of a strong magnet.
Okay.
Now, liquid nitrogen isn't normally magnetic, but each of the nitrogen molecules acts like a tiny magnet when it's exposed to a magnetic field. This effect is known as diamagnetism. That's just a fancy way of saying that each of the nitrogen molecules is repelled by the magnet's magnetic field. So, when I pour the liquid nitrogen past the magnet's poles, it doesn't look like anything special happens. The nitrogen just falls past the magnet. That's because the diamagnetic effect is very weak, so we don't normally observe it. All materials are at least slightly diamagnetic, but because the effect is so tiny, we don't normally notice it.
Just like nitrogen, oxygen isn't normally magnetic. And just like nitrogen, each molecule of oxygen behaves like a tiny magnet when it's exposed to a magnet's magnetic field. Oxygen behaves differently than nitrogen, though. The way oxygen behaves is called paramagnetism. That's a fancy way of saying that each molecule of oxygen is attracted to a magnet's magnetic field. So, when I pour the liquid oxygen between the poles of the magnet, it sticks. And we can even make a little bridge out of liquid oxygen that'll stay there until the oxygen finally boils away.
Thanks for watching. I hope you'll join us again soon for another experiment.
Let's try that with liquid nitrogen at the same time.
Okay.
Okay, so that was the magnetism of oxygen. So oxygen is attracted to the poles of a magnet. And so oxygen, experimentally, we know is paramagnetic rather than diamagnetic, which we would think because all of the electrons seem paired up, right? There's a lone pair of electrons, and when we think about a lone pair, we usually think about those as being paired up rather than unpaired electrons, which is what we need for paramagnetism. We need unpaired electrons. So let's take a look then at molecular orbital theory and how that plays out and how it helps us to talk about bonding in a slightly different way. Okay. And so when we look at molecular orbital theory, what we're essentially doing is we're saying, okay, we're going to take an atomic orbital on one atom and an atomic orbital on another atom and combine those two together to form molecular orbitals. It's very similar in theory to hybridization, except in hybridization, we took atomic orbitals on the same atom and combined them together. Here we're taking atomic orbitals on different atoms in the same molecule and combining them together. So just like in hybridization, if we start with two atomic orbitals, so atomic orbital 1 over here, atomic orbital 2 over here, this is hydrogen, and so I'm going to write H and H up top for our atoms, and then our molecule is H2, so I'm just going to write that up there. We have our two atomic orbitals, and for each atomic orbital, we should have a molecular orbital, right? We can't lose places to put our electrons, and so that was true in hybridization too, right? We took one s orbital and three p orbitals to make a total of 4 sp3 hybrid orbitals. Now we're going to take an s orbital from one hydrogen and an s orbital from another hydrogen, and we're going to make two sigma orbitals. Okay, and so here you see we have a sigma, and we just put a little 1s underneath it to signify sort of what the atomic orbitals were that orbital came from, molecular orbital came from. Up the top, we have sigma star 1s. Okay. Notice how the sigma is lower in energy than the atomic orbital, and the sigma star is higher in energy than the atomic orbital. When we talk about the lower in energy option, we call that a bonding molecular orbital. So this is a no star. This is just our sigma. And because the energy of that molecular orbital is lower than the energy of the atomic orbitals, that tells us that it's a more stable situation. And we know that anyway. We know that when bonds form, energy is released, right? We talked about bond energies at the tail end of chapter 9. And so we know that when a bond is formed, that energy is released and the molecule is more stable than the atoms by themselves. And so when those electrons go into a bonding molecular orbital, that's lower in energy than the atoms alone. Okay. The star orbitals up top, we call antibonding orbitals. And so this would be, we say star, like sigma star. Okay. This picture over here sort of shows that if we take two atomic orbitals and overlap them constructively, we get this overall molecular orbital here, where there's overlap of those two atomic orbitals. And up top, you see that there's absolutely no overlap between these, but in that molecular orbital, right? So there's no overlap, there's no bond, and so that's what we call anti-bonding. And it turns out that a bond and an anti-bond happen to cancel each other out, right? And so if we have an equal number of electrons in a bonding orbital as we have in anti-bonding orbitals, then we say that there are no bonds between those two atoms. So let's look at a few rules for molecular orbital configurations. The biggest rule, and that's the one that I've already said, is that if we're going to make new molecular orbitals, it has to be the same number of molecular orbitals as we had atomic orbitals. Okay. And so when we talk about taking a 1s orbital from hydrogen and another 1s orbital from a different hydrogen, that's two atomic orbitals, and so we should end up with two molecular orbitals, right? And so I'm just going to put in here that we can't lose spots for electrons. Okay. The other rule here is that if we have a stable bonding molecular orbital, then the corresponding anti-bonding molecular orbital is unstable. And we saw that again in the hydrogen molecule. But those should be equal to one another, at least in the examples we'll see. You see how this bonding, this sigma bond, the sigma 1s orbital is lower in energy, and it's exactly lower in energy as the sigma star is higher in energy. So those are sort of equal and opposite relative to the atomic energy. Okay. We're going to follow the Aufbau principle, right? Which, remember, tells us that we're going to fill from low to high. Each molecular orbital can accommodate up to 2 electrons. Still, quantum numbers apply, and so this rule is not new to us. We're going to use Hund's rule as we go when we add molecular orbitals of the same energy. So we'll see an example in a minute where we have molecular orbitals that are equal in energy. And then, of course, we can't lose any electrons, right? The number of electrons total in the molecular orbitals is equal to the sum of all the electrons in the bonding atoms. And so just like we can't lose spaces for those electrons, we can't lose electrons either. Okay. If we're going to make an ion or something like that, say we're going to make O2 minus. If we're going to make the O2 with a negative charge ion, then we essentially treat the 2 atomic orbitals, we treat one of them as O and one of them as O minus. And so we should always still have that extra electron in one of our atoms, so we add up to the right number of electrons in the molecular orbital diagram. All right, so for n equals 1, the molecular orbital diagrams look real easy. So we've got some molecules here, H2 plus, H2, helium-2 with plus charge, and then helium-2. And so we move from 1 to 4 electrons as we go on this path here. So with hydrogen-2 plus, we only start with 2 electrons, so when we lose 1, we only have 1 electron left. H2, that's the one we just saw, both electrons are in bonding orbitals. For helium-2 with a plus charge, we've taken away one of his 4 electrons, and so he only has 3 electrons. And then for helium-2, he's got all 4 electrons. I told you that the bonding and anti-bonding cancel each other out. And this equation here for bond order sort of shows us that. So the bond order, I'm going to rewrite this, is equal to 1/2 bonding electrons minus the non-bonding electrons. So bonding minus non-bonding, and then we just take a half because remember 1 bond is 2 electrons. And so they've calculated the bond order for us here below this image. If we just have 1 electron in a bonding orbital, then it's 1/2 times 1 minus 0, so that's just a half. For bond order for hydrogen, we end up with 1/2 of 2 minus 0, so that's 1. For bond order for helium-2 plus, it's 1/2 times 2 minus 1. And then this last one, here's where they completely cancel out. There's an equal number of bonding and anti-bonding, and there's no bond, right? Number of bonding equals the number of anti-bonding. And so when that happens, we end up with no bond. And that's why helium-2 doesn't exist, right? We don't see the helium is not diatomic. We don't see that in nature because there's no bond between those 2 atoms. And so again, this is something that this molecular orbital theory explains quite well. Okay. Now, as we move up to things with p orbitals, a lot of times we'll sort of ignore the S subshell because, again, if the S subshell is full, like we saw in helium, then the sigma bonding and the sigma antibonding all cancel each other out, and so we're left with no um, overall bond from the S orbitals, and so we sort of just ignore those because they don't really contribute. We also always ignore core electrons because those core electrons have an equal number of bonding and antibonding, and so they don't contribute at all to overall bonding as well. Okay. All right, and so this is the general scheme for molecular orbital configurations with things in the p subshell. And so we have our 3 p subshells on either side. And then in the middle, we have a sigma bonding and a sigma star antibonding. But we also have 2 pi bonding orbitals and 2 pi star bonding orbitals. Remember that anytime we form a bond between atoms, there can only be one single bond, sigma bond. And if we have a double bond, remember it's a sigma plus a pi. If we have a triple bond, remember it's a sigma plus 2 pi. And so the way that these molecular orbitals are named sort of lead us that direction to having those multiple bonds and having them already labeled as either sigma or pi. Okay. All right. So the next slide shows us. So let's do, for example, N2. Right? C2 we haven't really talked about, and there's no there's not a lot of evidence for it to exist. Carbon is not one of our diatomic elements, but nitrogen is. How many valence electrons in the p subshell for each nitrogen atom?
Is it 3?
3, that's right. So nitrogen has 5 valence electrons. 2 of those are in the S subshell, 3 of those are in the P. And so if we put a nitrogen atom on each side and N2 in the middle, we end up with 1, 2, 3 for nitrogen, 1, 2, 3 for nitrogen. And so I have a total of 6 valence electrons here in my molecule that I'm going to put in. I'm going to follow Hund's rule, remember. 1 and 2, 3 and 4. And remember, spread them apart, spread them across the different orbitals of the same energy first, then go back and pair, so there's 4, 5, and 6. And so if we look at the bond order, we've got 1/2 times, well, there's 6 bonding, and there's no electrons up here in the anti-bonding. And so the bond order for nitrogen is 3. And we know nitrogen has a triple bond. Okay. And so, again, molecular orbital theory is good at indicating this for us. I'm going to erase this real quick and do oxygen, since we talked about oxygen already, as being one of those things that doesn't exactly follow hybridization rules very well. If this is oxygen and this is oxygen and this is O2, how many electrons are in the 2p subshell for oxygen?
4.
4, that's right. And so we end up with 1, 2, 3, 4 for each oxygen atom. That gives us a total of 8. And if we go to fill in our molecular orbital diagram, 1, 2, 3, 4, 5, 6. Now I have to jump up to the antibonding. I'm going to go to the next lowest energy. That's alpha principle. I'm going to spread those last 2 electrons across across those same energy orbitals. That's Hund's rule. And now we see that O2 does in fact have two unpaired electrons. Right? Two unpaired electrons makes it paramagnetic. And that's the behavior that we saw in the video. Okay. So we see that the molecular orbital diagram, molecular orbital theory, really does help us describe the bonding of some of these molecules. Molecular orbital theory gets much more complicated as soon as we have more than two atoms, as you can imagine, because it's not just left and right, what does the center make? It's much more complicated in terms of how the different atomic orbitals can interact with one another, how they constructively and destructively interfere with one another. And so when we go about trying to figure out what the molecular orbitals are on larger molecules, we use computational assistance. We figure out all the possible combinations of atomic orbitals. Those are called linear combinations of atomic orbitals, LCAOs. You might have seen that term in Alex homework. If you have p orbitals from two electrons, from two atoms, it's easy to see that maybe you have some bonding orbitals down here. Remember, these overlap like this, right, with our two nuclei in the middle. And for the antibonding, if those are two nuclei, remember that they do not overlap at all. They are separate. They're trying to get away from one another. And so the antibonding orbitals don't overlap, the bonding orbitals do. And so again, you may have seen that LCAO term, linear combination of atomic orbitals. It's easy to do when we have two atoms, much more difficult even when we just add one extra atom, not to mention when we're talking about molecule with dozens or even hundreds of atoms. Okay. So we're going to stick to two atom molecules. So N2 plus is an ion, and we can think about the molecular property, the properties of N2 plus if we think about the molecular orbital theory. So this is 2p, this is 2p. We know that we're going to have some pi 2p's and some sigma 2p's, pi star 2p, and sigma star 2p. And so remember, I told you that when we make an atom, an ion, we need to make one of those two atoms our ion with plus or minus the number of electrons. And so it doesn't matter if you do that on the left or on the right. I'm going to make this one my plus. And so if he's a plus, he has one fewer electron. We've already said nitrogen should have 3 in the 2p, so he should just have 2 in the 2p. This guy will have 3. Right? And so I'm going to give you just a minute to work on that and figure out the answers to those 4 problems. So for part A, we will come back to that in just a minute. I haven't fully gone through how to do that one. But how about the bond order? What did you figure out to be the bond order for N2 plus?
5/2.
Yeah, 5 halves, excellent. So when we load this in, we should have 1, 2, 3, 4, 5 electrons, right? 5/2 is great. If you said 2.5, that's also fine. All right, how about our magnetic properties? Well, does our molecule have any unpaired electrons?
Nope.
No?
Oh, missed that one.
Yeah. And so we have an unpaired electron. And so does that make it diamagnetic or paramagnetic?
Paramagnetic.
Paramagnetic, for sure. So the bond length relative to N2, well, we already calculated the bond order for N2 to be 3. This one has a bond order of 2.5. And so what does that tell us about the bond length?
It's longer.
It's longer, yeah. So remember, the higher the bond order, the closer together those nuclei have to be. And so the shorter bond, the higher the bond order. So since this is a bond order of 2.5 versus 3, it's going to be a little bit longer. Right? So tell me about the bond strength rather than the bond length. Is this bond going to be stronger or weaker?
Weaker.
Yeah. So it's also going to be a weaker bond. Okay. Now I'm going to come back up to this electron configuration. I'm going to move to the next slide. You don't have another blank slide, but I'm going to cover molecular orbital electron configurations here real quick. So electron configuration for molecules with using molecular orbital. So for N2 plus, we didn't draw the 1s or the 2s. We only drew the 2p, but we can't ignore those 1s and 2s orbitals. So I'm going to draw out the whole thing real quick, and then I'll show you, what the shortcut is. But there's our 1s, there's our 2s, there's our 2p. Again, this is N plus and N, and then in the middle we have N2 plus. So we have the sigma 1s and the sigma star 1s. For the 2s subshell, we have the sigma 2s and the sigma star 2s. And then for the 2p subshell, we have our pi 2p's and our sigma 2p's, or 2p, only one of those. Then we have our pi star 2p and our sigma star 2p. And so we know that this one has a total of 6 electrons because he's a plus. The nitrogen atom has 7 electrons, so he looks like that. And again, we're going to follow the Aufbau principle. We've got a total of 13 electrons. We're going to just load them up from the bottom. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Let me draw some sort of dotted lines here. Right, so here, these are our core electrons, and these are our valence electrons. And so anytime you have a set of core electrons, you know that all those molecular orbitals are full, so you have to have an equal number of bonding and antibonding. And so what it looks like would be sigma 1s with 2 electrons in it, right? So that orbital is called a sigma 1s orbital. And just like we did 1s2, 2s2, 2p6 kind of thing, we're going to do sigma 1s 2, sigma star 1s 2. Our 2s molecular orbitals are also completely full. And so we know we're going to have sigma 2s 2, sigma star 2s 2. And then for our our 2p molecular orbitals, we've got our pi 2p with a total of 4 electrons. The textbook sort of talks about separating out the x versus the y versus the z. To me, there's no reason to do that. We're going to focus just on the pi versus sigma bit. And then our sigma 2p has just 1 electron in it. So he's going to be sigma 2p1. And so that's our electron configuration for N2 plus. Now, if I wanted to do just N2, the only thing that changes is an electron in that last shell, that last orbital. And so we know there's going to be sigma 1s to sigma star 1s to sigma 2s to sigma star 2s to pi 2p 4. And then if we're going from a positive ion to a neutral, we're adding an electron, and so he must be a sigma 2p2, like adding 1 more electron to that highest energy orbital. And so those are the electron configurations when we talk about molecular orbital theory. All right. The very tail end of chapter 10 talks a little bit about how molecular orbitals are not just across 2 atoms, they're across lots of atoms. And while those are good things to know, that we're not going to spend a lot of time looking at that. But that's something that you talk much more about in organic and physical chemistry, how those molecular orbitals carry on across the whole molecule rather than just on a pair of atoms. Okay. All right. That is the end of chapter 10, and that's the end of the ALEKS material for this week. Wednesday, we will, I'll be happy to answer any questions about ALEKS, about the final exam. And, you know, we may do some review, bring questions from all 10 chapters if you'd like. Thursday, we will meet for lab. We're going to dip our toes into chapter 11 and talk about intermolecular forces. We talked a tiny bit about intermolecular forces in chapter 5 when we talked about the difference between real and ideal gases. But we're going to talk more about the intermolecular forces and the different types of intermolecular forces on Thursday in lab. The quest will be just like it was before the break. It'll open at noon, be open until 3:30. We will meet together at 3:30 for a short little lecture and then do a class cake activity on intermolecular forces. Okay. All right, well, feel free to hang around if you've got any questions, but other than that, I hope you have a good Monday, and I hope it's not quite as rainy where you are as it is here in Spartanburg.
Thank you.
Thank you so